In the previous mini lectures, we developed the concept of fluid head, which is a measure of the energy of a flow at a given state. We observed that for an idealized flow with no losses or work or heat addition, the total fluid head does not change, even though the velocity, pressure, or elevation may change. Two effects that can change the total head of a fluid are work, such as pumping, or friction. In the last video, we explored the change in fluid head associated with pumping. In this video, we will work with the changes in fluid head due to friction losses in pipes. For any real fluid, the effect of friction is to reduce the total fluid head. Let's start by writing the energy balance for a steady flow in a pipe with friction. We can treat the friction effect as a heat transfer rate rather than work. Intuitively, we can think of this as the effect of rubbing your hands together, or the brakes on a car. The result of the friction force can be treated as a force times a distance, or as a heat transfer. An energy balance would show that they were equal. We'll use a heat transfer model here because it will give us additional insights into the friction effect at the end of the analysis. Similar to the previous analyses, we solve for the heat transfer rate divided by the mass flow rate. Again, we substitute the definition of specific enthalpy as a specific internal energy plus the pressure divided by the density. In contrast to the previous analyses, we cannot assume that the specific internal energy remains constant because this process includes losses. Rearranging, we arrive at the pressure at station 1 divided by the density times the acceleration due to gravity plus the velocity at station 1 squared divided by 2 times the acceleration due to gravity, plus the elevation at station 1, all equal to the same terms at station 2, plus the specific internal energy at station 2, minus the specific internal energy at station 1, minus the heat transfer rate divided by the mass flow rate, all divided by the acceleration due to gravity. Inspecting, we see that the left-hand side is the total head at station 1, and the right-hand side is the total head at station 2, plus this remaining term, which we call the head loss. We can show that the head loss term is always greater than or equal to 0. This tells us a bit about the effect of friction on a flow. Treating the pipe as insulated, we see the specific internal energy of the flow must increase as a result of friction. For an incompressible substance, this means that the temperature increases. If instead we assume the temperature does not change, we must have a heat transfer rate out of the flow. Either way we look at it, friction converts the useful pressure, velocity, and elevation head into a less useful increase in temperature, or a heat transfer out, reducing the useful energy, or head, of the flow. One way of looking at this head loss is that it is the elevation change we would need to include between station 1 and station 2 in a frictionless flow to achieve the same result. Friction introduces a loss that must be overcome to maintain the flow. We rarely use the definition of friction head that we arrived at above. In practical applications, it is much more useful to relate the losses to the friction shear forces. These forces can be correlated for any pipe flow using the Reynolds number and the effective roughness. Let's start with a fully developed flow in a horizontal pipe. The flow is steady, and friction acts on the fluid over the flow length L. We can draw a free body diagram on the fluid within the pipe and perform a force balance. At station 1, we have the fluid pressure acting over the area. At station 2, we also have the fluid pressure acting over the area. Finally, along the walls of the pipe, we have the shear stress tau acting over the entire surface area of the pipe. Writing Newton's second law, for a steady flow, the mass balance reduces to the mass flow at station 1 equal to the mass flow at station 2. For a constant area pipe and an incompressible flow, we see that the velocity at station 1 is equal to the velocity at station 2. For a viscous flow, the velocity changes as a function of radius within the pipe, giving us the familiar velocity bullet associated with fully developed internal flow. This means that the velocity from the mass balance is an average velocity over the flow area of the pipe. Writing Newton's second law, we have the acceleration equal to 0 because the flow average velocity does not change. The sum of the forces is P1 times the area minus P2 times the area minus tau wall times the area of the wall, all equal to 0. The flow area is pi times the diameter squared divided by 4. The area of the wall is pi times the diameter times the length. Substituting into the force balance, we see that the change in pressure is equal to 4 times the wall shear stress times the length divided by the diameter. Note that this applies for any fully developed internal flow, whether it's laminar or turbulent. We can also apply the conservation of energy to this flow in the form developed earlier. We have the total head at station 1 equal to the total head at station 2 plus the head losses due to friction. For this pipe, the flow is level and the velocities are equal. The energy balance tells us that the change in pressure is equal to the head loss times the density times the acceleration due to gravity. We also see that the head loss is equal to the change in pressure divided by the density times the acceleration due to gravity. Combining the previous results, we see that the head loss due to friction is equal to 4 times the wall shear stress divided by the density times the acceleration due to gravity, all times the length divided by the diameter. This is the height that must be overcome in an inviscid flow to simulate the effect of friction. This head loss can be used in an energy balance of the form head at station 1 equals head at station 2 plus head loss. Calculating the head loss using the definition we've just arrived at requires us to first compute the wall shear stress. If we know the velocity profile within the pipe, we can use the definition of shear stress, tau equals mu du dy, to compute the shear and sub into the head loss. Often, computing the velocity profile is inconvenient. Instead, we correlate the wall shear using Reynolds number and the effective roughness. We define a friction factor using dimensional analysis. The logic that leads to the friction factor definition is similar to the development of the Reynolds number. The friction factor is defined using the change in pressure is equal to the friction factor F times the length divided by the diameter times 1/2 density times velocity squared. Once we have a friction factor, we can return to the definition of friction factor to compute the head loss, which can then be used in the energy balance that we derived above. We have the head loss equal to the friction factor times L over d times the velocity squared divided by 2 times the acceleration due to gravity. The friction factor, F, can be found in empirical relations such as the Moody Chart. The Moody Chart is available in any fluid mechanics text, such as Figure 820 in the 6th edition of Fluid Mechanics by Munson. For a given Reynolds number and surface roughness, we can look up the friction factor for the flow and compute the head loss. The Moody diagram shows that for a laminar flow, the friction factor does not depend on the roughness. In general, the friction factor is equal to 64 divided by the Reynolds number. For turbulent flow, the roughness becomes significant, and we must use the Moody diagram to find a friction factor. Repeating the energy balance, we have the total head at station 1 equal to the total head at station 2 plus the head loss. We can use this to solve combined change in pressure, height, and velocity situations with friction. Another use of the friction factor is to correlate losses using dimensionless groups. The result is that we can test a section of pipe in a lab setting and use the results for a different size pipe, provided that the Reynolds number matches. We can use the Moody diagram for this purpose and compute the friction losses in any pipe for the system we are interested in. That concludes the mini lecture on friction factor. Thanks for tuning in and have a great day.